Yes, sir, they're visible.
Okay. Yeah, in real life, you might have come across the data structures. Today, I'm going to brief about data structure and algorithms. So, data structure can be defined as the group of data elements, so which can provides an efficient way of storing and organizing data in the computer, so that it can be used efficiently by any of the application. Some examples of data structures are arrays, linked list, stacks, queues, etc. So you are going to deal about all these data structures in the coming classes. Data structures are widely used in almost every aspects of computer science. Say for example, operating system, compiler design, artificial intelligence, graphics, and also many more. Data structures are the main part of many computer science algorithms, as they enable the programmers to handle the data in an efficient way. It plays a vital role in enhancing the performance of a software or a program, as the main functions of the software is to store and retrieve the user data as fast as possible. Before discussing the data structure in detail, let us see some of the basic terminologies which we are going to use repetitively in the ongoing classes. Data structures are the building blocks of any program or the software. Selecting the appropriate data structure for a program is the most difficult task for the programmer. So some of the basic terminologies which are we going to use are listed and as follows. The first one is nothing but a data. Data can be defined as an elementary value or a collection of items. Say for example, a student name and its ID are the data about the student. The second terminology is nothing but the group items. Data items which have subordinate data items are called group items. Say for example, if the student name is an example for the group items where you can able to find the first name and the last name in this name. Next terminology is what a record. Record can be defined as the collection of various data items. Say for example, if we talk about the student entity, the student name, address, course, and marks can be grouped together to form the record for the student. The next one is a file. A file is a collection of various records of one type of entity. Say for example, if there are 60 employees in an organization, then there will be 20 records in the related file where each contains the data about each employee. Next one is nothing but attribute and entity. An entity represents the class of certain objects. It contains the various attributes. Each attribute represents the particular property of that particular entity. The last terminology is nothing but a field. Field is a single elementary unit of information representing the attribute of an entity. So these are some of the terminologies we are going to use when you are going to deal with the data structures. The next question is, what is the need of the data structures? As you know, today the applications are getting complexed and the amount of data is increasing day by day. So there may be arise the following problems. The first problem is nothing but the processor speed. To handle large amount of data, the high speed processing is required. But as the data size is growing day by day to the billions of files per entity, the processor may fail to deal with that much of huge data. So in order to overcome this problem, we need to represent our data in the form of a data structures. Second one is a data search. Say, let us consider an example of an inventory where it has a size which is equal to, say, for example, 10,000 items. Means that there are 10,000 items in a store. Suppose if our application needs to search for a particular item, it needs to traverse through all the 10,000 items every time. This process slows down the search process. The second reason is multiple requests. If thousands of users are searching the data, specific data simultaneously on the web server, then there are the chances that very large server can be failed during that process. In order to solve the above problems, so data structures are used. So data is organized to form a data structure in such a way that all items are not required to be searched and required data can be searched instantly. Now let us see the advantages of data structures. The first advantage of using a data structure is the efficiency. The efficiency of a program depends upon the choice of the data structure. What kind of data structure you are going to use for your application, that is going to decide the efficiency of that data structures. For example, suppose if you have some data and we need to perform the search for a particular record. In that case, if we organize our data in an array, we will have to search sequentially element by element. Hence, using array may not be very efficient here. Say for example, suppose if I have given a array which consisting of 100 elements, the data to be searched may be located at the end of the array, so that you need to traverse through all the elements from the beginning, so that you are representing the data by using the arrays may not be efficient. But there are better data structure which can make the search process efficient, like ordered array. Say for example, you have given an item, those items can be stored in the ordered array. They might be in the ascending order or the descending order. If the data are arranged in the order way, it is very easy for searching. The next one is nothing but reusability. So data structures are reusable, means that once we have implemented a particular data structure, we can use it at any other place. Implementation of data structure can be compiled into libraries which can be used by different clients. So next one is nothing but abstraction. Data structure is specified by the ADT, which provides a level of abstraction. The client program uses the data structure through interface only, without getting into the implementation details. So these are the some of the advantages we can get if our data are arranged by using the data structures. This slide show you the classifications of the data structures. Basically, there are two types of data structures. The first one is primitive data structure. The second one is non-primitive data structure. The primitive data structures are primitive data types, which we have discussed. They are nothing but int, char, float, double, and pointer. So these are the example for the primitive data structure. These data structure, primitive data structure, can able to hold a single values. Next, we have a non-primitive data structure. The non-primitive data structure again divided into the linear data structure and as well as the non-linear data structure. Coming to the linear data structure, a data structure is called linear if all of its elements are arranged in the linear order. That is the name, the linear data structure. In linear data structure, the elements are stored in non-hierarchical way, where each element has the successor and predecessor except the first and as well the last elements. So these things you will discuss in the linked list chapters. So under this linear data structure, we have an arrays. We have already discussed about an array. An array is nothing but a collection of similar type of data elements, and each data item is called an element of that particular array. Next, we have a linked list. The linked list is an example of linear data structure which is used to maintain a list in the memory. It can be seen as the collection of nodes stored at non-continuous memory location. Suppose if you look at the arrays, all the elements are stored in the consecutive memory location, but this is not in case of the linked list. So that we are going to make the nodes for storing the record. So these nodes can be located anywhere in the continuous memory location, but not in the consecutive locations. So each node of the list contains a pointer to its adjacent nodes. Say for example, the nodes for the linked list can be represented by using the following fields. Say for example, I have a data field, I have a front field and I have the rear field. These two are nothing but the pointer fields. Okay, so these pointer fields are used to hold the address of the next node and as well as the address of the previous node, so that it is not required to store the nodes or the linked list in the continuous memory location. They can be distributed over the available memory space in the computer memory. The next we have a stack. It is a linear list in which the insertion and deletions are allowed only at one end. So that end is called start. Some of you can mute your microphone. It is named as a stack because it behaves like a real world example. Say for example, example for this is files of plates or a deck of cards, etc. The next linear data structure is nothing but an queue in which elements can be inserted at only one end called the rear end and deleted only at the other end called the front end. It is an abstract data structure. It is similar to the stack only. The queue is opened at both the ends. So therefore, it follows the following methodology. So that is nothing but first in, first out methodology for storing the data items. Next, we have a nonlinear data structure. This data structure does not form a sequence. That is, each item or element is connected with two or more other items in nonlinear arrangements. The data elements are not arranged in sequential structure in case of the nonlinear data structures. The example for nonlinear data structures are trees and graphs. The trees are multi-level data structure with a hierarchical relationship among its elements called nodes. The bottommost nodes in each hierarchy called leaf and the topmost node in the tree is called root node. So we are going to discuss all these, okay, so in the tree binary trees chapters in details. Next we have a graphs. The graphs can be defined as the pictorial representation of the set of elements connected by links. Those links are called as edges. A graph is different from tree in the sense that a graph can have cycle while tree cannot have the one. So you will see the difference between the trees and graphs in the coming chapters. Now let us see what are the operations we can able to perform on the given data structure. The first and foremost the operations we can perform on the data structure is nothing but the traversing. Every data structure contains the set of data elements. Traversing the data structure means visiting each element of the data structure in order to perform some specific operation like searching or sorting. Say for example, if we need to calculate the average marks of the student in 6 different subjects, we need to traverse the complete array of marks and calculate the total sum. Then finally, the average can be obtained by dividing it by 6. So in order to find the average, we are going to find the sum and finally we are going to divide it by the total number of subjects. Next operation is nothing but insertion. Insertion can be defined as the process of adding the elements to the data structure at any location. Say for example, you already have a pre-existing data structure. So this insertion operation allows us to add element either at the beginning or at the end or at the specific locations. If the size of the data structure is n, suppose if the size of the data structure is n, then we can only insert n minus 1 data elements into it, n minus 1 data element into it. Next operation is nothing but deletion. The name implies that it is nothing but the process of removing an element from the data structure. We can delete an element from the data structure at any random location. Say for example, the first item can be deleted or the last or any specific item in the data structure can be deleted. The next operation is searching. The process of finding the location of an element within the data structure is called the searching. So there are basically two algorithms to perform the searching. The one is called as linear search and second one is binary search. We will discuss each one of them later in the coming chapters. Next operation is nothing but sorting. It is nothing but the arrangement of data structure in a specific order. There are many algorithms are used to perform sorting. Say for example, you might have come across some of the algorithm like insertion sort, bubble sort, merge sort, and so on. Many more algorithms are there for performing the sorting operations. So again, we have a separate chapter on sorting and we'll be discussing all these things one by one. Next, the last algorithm is nothing but, last operation on the data structure is nothing but merging. Suppose when two lists, suppose you are given a list A and B of size m and n, say for example, the size of A is n and size of B is n. These lists have a similar data elements. If you wanted to club or joined to produce the final list or the third list, we can able to make the operation that is nothing but the merging operation. Okay, these are some of the operations we can able to perform on the data structures. Okay, next is an introduction algorithm. Let us see what is an algorithm here. An algorithm is nothing but a process or set of rules required to perform calculations or some other problem solving operations, especially by a computer. The formal definition of an algorithm is that it contains the finite set of instructions which are being carried out in a specific order to perform the specific task. It is not the complete program or code, it is just a solution of a program which can be represented either as an informal description using a flowchart or the pseudocode. The sum of the characteristics of an algorithm are shown in this. The first character is nothing but an input. An algorithm has some input values. We can pass 0 or some input value to an algorithm so that the input should be well defined for any given algorithm. The second one is nothing but an output. The algorithm can able to produce either one or more outputs at the completion or at the end or completion of an algorithm. Again, the output for the given algorithm should also be well defined. The third characteristics of an algorithm is nothing but an unambiguity. An algorithm should be unambiguous, which means that the instructions in an algorithm should be clear and simple. The fourth characteristics of an algorithm is nothing but finiteness. An algorithm should have finiteness. Here, finiteness means that the algorithm should contain a limited number of instructions. That is, the instruction should be countable. The fifth characteristics of an algorithm is nothing but effectiveness. An algorithm should be effective as each instruction in an algorithm affects the overall process. The last characteristics of an algorithm is language independent. An algorithm must be language independent so that the instructions in an algorithm can be implemented in any of the languages with the same desired output. Now let us see how the data flow takes place in an algorithm or how algorithm can be used for solving the given problem. The first one is nothing but the problem statement. A problem can be a real world problem or any instance from the real world problem for which we need to create a program or the set of instructions. The set of instructions is known as an algorithm. The next is an algorithm. An algorithm will be designed for the problem, which is a step-by-step procedure. So, as we have discussed in the previous slide. Next, we have an input. After designing an algorithm, the required and desired inputs are provided to the algorithm. So next is the processing unit. Your inputs will be given to the processing unit and the processing unit will produce the desired output for the given problem. The next one is nothing but an output. The output is the outcome or the result of the programs. So next question arises, why do we need an algorithms? The algorithms are needed for scalability purpose. It helps us to understand the scalability. Say for example, when we have a big real world problem, we need to scale it down into a small steps to easily analyze the problems. The second point is performance. The real world is not easily broken down into smaller steps. If the problems can be easily broken into smaller steps, means that the problem is feasible. Let us understand the algorithm through a simple example. Suppose we want to write an algorithm to add two numbers entered by the user. So this is an algorithm. The given problem that the addition of two numbers is represented by using the algorithm steps which are given as shown here from step 1 to step 6. In order to perform the addition of two numbers, okay, so I have to start it. After starting it, we need to declare the variable which is required for carrying out the defined given problem. That is, I wanted to add two numbers, so that I need to declare two variables and also another variable for holding the sum of these two numbers. Once the variables are declared, in the next step, you need to require the value for the variables A and B. So in the fourth step, we are going to add the values A and B, and your result will be stored in the variable sum. So sum is equal to A plus B. And finally, we are going to print the sum, or we are going to store the sum either in the file or in the some other variables. And finally, we are going to terminate the process in the step 6. As in the above example, we can able to directly compare this definition to an algorithm. We cannot perform, say for example, step 4. The step 4 cannot be performed before the step 3. Means that we need to follow the specific order to make or to find the sum of two numbers. Without having the values for addition, it is not at all possible to obtain the sum of these two numbers. In case of algorithm, it is very much important to follow a specific order while solving the problems. Now let us look at the factors of an algorithm. What are the factors which will influence the design of an algorithm? The first factor is nothing but the modularity. If any problem is given and we can break that problem into small modules, which is a basic definition of an algorithm. It means that this feature has been perfectly designed for the algorithm. So in the sense that the given complex problem can be a problem, or the module can be divided into the number of submodules where each submodules can be independently implemented. The second one is nothing but the correctness. The correctness of an algorithm is defined as when the given inputs produce the desired output, which means that the algorithm has been designed so that we can able to get the well-defined output. The analysis of an algorithm has been done correctly. The third factor is nothing but maintainability. Here, the maintainability means that the algorithm should be designed in a simple, structured way so that when we define the algorithm, no major changes will be done in the algorithm. The next factor is functionality. It considers various logical steps to solve the given real world problems. Next one is robustness. So robustness means that how an algorithm can clearly define our problem. So next factor is nothing but user friendly. If the algorithm is not user friendly, then the designer will not be able to explain it to the programmer. The next factor is nothing but simplicity. If the algorithm is simple, then it is easy to understand by XYZ. The last factor is nothing but extensibility. If any other algorithm designer or a programmer wants to use your algorithm, then it should be extensible. Let us see the importance of algorithm. The first importance of an algorithm is theoretical importance. When any real world problem is given to us and we break the problem into small modules, to break down the problem, we should know all the theoretical aspects. Means that for what exactly we are going to break the modules into smaller one, and how that can be combined together into the main modules. The second importance of an algorithm is practical importance. As we know that theory cannot be completed without the practical implementation. So the importance of algorithm can be considered as both theoretical and as well as the practical. So next is algorithm analysis. Okay, this is analysis of algorithms are very much required in order to compare the different algorithms. The algorithm can be analyzed in two levels. That is, first is before creating an algorithm. The second is after creating the algorithm. So there are the two analysis, two ways you can able to analyze the algorithm. Analyze the algorithm. The first one is nothing but priori analysis. Second one is posterior analysis. If you take the priori analysis, here priori analysis is the theoretical analysis of an algorithm which is done before implementing the algorithm. Various factors can be considered before implementing the algorithm, like processor speed, which has no effect on the implementation cost. The next analysis is nothing but the posterior analysis. Here, posterior analysis is the practical analysis of an algorithm. The practical analysis is achieved by implementing the algorithm using any programming languages. The analysis basically evaluate that how much the running time and the space is taken by the algorithm during the execution. So next is algorithm complexity. The performance of the algorithm can be measured in two factors. The first one is nothing but the time complexity. The second one is nothing but the space complexity. So these are the two factors. So by using these two factors, the complexity of the designed algorithm can be studied. The first factor is nothing but the time complexity. The time complexity of an algorithm is the amount of time required to complete the execution. The time complexity of an algorithm is denoted by big O notation. We will be discussing this one in the coming slides. Big O notation. Here, the big O notation is the asymptotic notation to represent the time complexity. The time complexity is merely calculated by counting the number of steps to finish the execution. Mean that by counting the number of instructions in the program, it is possible for you to analyze what is the time taken by all the instructions in the algorithm. So let us consider the example. By using this example, we can able to calculate the time complexity of this. Say for example, we wanted to find the sum of numbers. Initially, I am going to initialize the variable 0. Here I have a for loop. Here I am going to find the sum of the numbers from 1 to n. So I'm going to find it and I'm going to return the sum. I mean that assume that okay, this is a function. So this function is going to return the sum of some integers up to n. In this code, the time complexity of this loop statement will be at least n in this case. And if the value of n increases, then the time complexity also increases. While the code complexity of the code, that is the return sum, will be constant as its value is not dependent on the value of n. If you look at this one, this statement does not depend upon the value of n. It is going to return the value sum to the calling program. But here the time complexity of this code particularly depends upon the n value. Suppose if n value increases, the number of iteration which you are going to perform also increases. Means that this statement will be executed n number of times. We generally consider the worst time complexity as it is the maximum time taken for any given input size. Say for example, if you wanted to find out the time complexity, we are going to consider the worst case value, that is the maximum value for the n. Okay, that is what the big O notation is going to give. We will discuss these big O notations and other notations in the coming sections. So next we have a space complexity. For any given algorithm, okay, we need to consider the space complexity also, okay, because we are going to build an algorithm, okay, either it should be time constraint or it should be space constraint. So an algorithm's space complexity is nothing but the amount of space required to solve a problem, and means that how much of space is required by the algorithm in order to store the code for that. Similar to the time complexity, the space complexity is also expressed in the big O notations. Okay, as we discussed here, big O notations is also used for representing the space complexity. For any given algorithm, the space is required for the following purposes. The first one is nothing but to store the program instructions, whatever the instructions you are writing to solve the given problem. Okay, we need some space for storing your instruction, and your program or algorithm may be using some set of constant value. You require some memory space to store these constant value. Then to store the variable values, you may be using the algorithm may be using the some set of variables. You require some space for these variables, and also to track the function calls and also jumping statement. Okay, so that for any given algorithm is required the space for these four things. So next is asymptotic analysis. As we know that data structure is a way of organizing the data efficiently, and that efficiency is measured either in terms of time or space. So the ideal data structure is a structure that occupies the least possible time to perform all its operation and the memory space. Our focus should be on finding the time complexity rather than the space complexity. By finding the time complexity, we can decide which data structure is the best for the algorithm. The main question arises in our mind that on what basis should we compare the time complexity of data structures. The time complexity can be compared based on operations performed on them. Let us consider an example in which we try to insert a new element at the beginning of the arrays. Suppose we have an array of 100 elements. We have an array of 100 elements, and we want to insert a new element at the beginning of the arrays. Say for example, this is our array. Have a subscript values from 0 to 99, and I wanted to insert the new element at this point. At this point, I wanted to insert the new element. In order to insert the new element, so you need to perform a shifting operation here. This is going to become very tedious task, as we need to shift the element towards the right, and we will add the new element at the starting of the array. Say for example, if you want to insert a new element at the first location, so that the element at the 99th location should move to the 100th location, and 98 should go to the 99, and so on here, you need to perform 100 shift operation. At the end of this shift operation, the first element becomes vacant, so that we can able to insert the new element. So this is what we can able to perform if the data are stored by using the arrays. The second one is, say for example, you may be using the linked list. We wanted to add the new element at the beginning of the linked list. Say in case of linked list, your data are stored by using a node. The node has a different field, say for example data field and front pointer and as well the rear pointer. So you may be having a data structure like this. Okay, so the main function of the
these pointer fields are used to hold the address of the other nodes. Say for example, this may be pointing the front of the next node, and this going to pointing to the first of the pointing to the next node, okay, and so on. Say for example, here there is no prior node for this first node. 1, 2, 3, 3 nodes I have here, so this becomes empty, and there is no fourth node here. This field becomes null here, so that this is going to hold the values this way. Say for example, if you wanted to add the new element at the beginning of the array, you need to change the pointer value, so that in this pointer field you need to store the address of the first node. Okay, this fourth node is going to become the first node here. This field becomes null, this pointer field becomes null, and you have a data over here. This is how we can able to do that one. Okay, so that compared to the array kind of data structure, so linked list is very much useful for inserting the elements. You don't require to do the much operation what we have done for the arrays, that is the shifting operation. The same thing holds good for deleting the elements are also. The next is analyzing the algorithm, finding the time complexity or the running time of an algorithm. The measuring of the actual runtime is not practical at all. The runtime the running time to perform any operation depends upon the size of the input. Okay, let us consider this example. To add a new element at the beginning of the arrays, say for example, I have a arrays, and I have a, say for example, 5 elements, 0, 1, 2, 3, 4. These are the first element. Sorry, these are the index values. 22, 33, 44, and 55. Say for example, we have over here. Suppose we want to add a new element at the beginning of the array. To achieve this, we need to shift each element towards the right here, so that I supposed to move the 55 to this location, and 44 to this, 32, 22, and 11, and I need to add the new element, say for example 99 to this location. This is what I supposed to do for this. Okay, say for example, in this example we have 5 elements, so 5 units of time would be taken. Say for example, 5 unit of time I am considering it. Unit of time is, it may be one, say for example 1 nanosecond. For shifting one element, if you require 1 nanosecond to shift the 5 elements, actually you require a 5 nanosecond times to do these operations. Okay, suppose if the data set contains only few elements, okay, so that this 5 nanosecond is not an does not impose any critical things over the operations. But suppose if there are huge amount of elements are there in the array, say for example I have a 10,000 elements in the array. If you wanted to insert the first element at the 10th first new element at the beginning of the array, we need to perform 10,000 shift operation. If each shift takes 1 nanosecond, so in order to shift 10,000 element, 10,000 nanoseconds is required. 10,000 nanoseconds of time is required. So it concludes that the time complexity depends upon the input size. As your input size grows, okay, time complexity of an algorithm also grows. So therefore, if the input size is n, then the function f of n is a function of n that denotes the time complexity. So next is calculating the function f of n. Calculating the value of function f of n for a smaller program is easy, but for bigger program it is not that easy. We can compare that data structure by comparing their f of n values. We can compare the data structure by comparing their f of n values, so we can able to find the growth rate of f of n, because there might be a possibility that one data structure for a smaller input size is better than the other one, but not for the larger size. Let us consider this particular example. I have a function f of n. The function f of n is a function of n and it is given by 5n square plus 6n plus 12. Let us consider this example with the n value is equal to 1. I wanted to find out the runtime of each and every term separately. I want to find the percentage of running time for the term 5n square. Okay, that can be calculated as 5n square divided by 5n square plus 6n plus 12 here. If n is equal to 1, this becomes 5 plus divided by 5 plus 6 plus 12 into 100, that is 21.74%. Mean that 5n square takes this much of time. Okay, so mean that 21.7% of the time is taken by the 5n square. So percentage of running time due to the term 6n is nothing but 6 divided by 5 plus 6 plus 12. Since n is equal to 1, this will be 26.09%. So similarly, for the last term, okay, the 12, the runtime will be calculated here. It is nothing but 12 divided by 5 plus 6 plus 12 into 100. It is 52.17 17% of the total time. From these calculations, it is observed that most of the time is taken by the constant term 12 here. Okay, here the 52.17% of the time is among the total time is taken by the last term, that is the constant term 12 only. Okay, for the value n is equal to 1, but we have to find the growth rate of f of n. For different values of n, we'll see how exactly 5n square and 6n and 12 behaves. Okay, suppose if n values keep increases, the growth rate is calculated and it is shown in table. Initially, n value is equal to 1. We have calculated the growth rate of 5n square, 6n and 12 for n is equal to 1. This is going to be 21.74%, 26.09 and 52.1%. For n is equal to 2, the first term is going to, the share of the first term is itself 87.41%, and 6n is nothing but 10.49%, and 12 is nothing but 2.09%. And for n, for 100, it is 98, 1.19 and 0.02%. Similarly, for 100, 99.88% is taken by the term 5n square, and 0.12% by the 6n, and 0.002% by the 12. So as we can observe in the table that the increase in the value of n, the running time of the 5n square, increases while the running time of 6n and 12 also decreases. If you can able to see here, the runtime is keep increases here. The runtime for this keep decreases as n value increases. And it is observed that for larger values of n, okay, say for example larger value of n, say for n is equal to 100, the square terms it consumes almost 99% of the time, as the term n square is contributing most of the time, so that in the algorithm analysis we are going to consider the term which contributes more compared to the other terms. Say in this case we can eliminate the two terms 6n and 12. The contribution by the 6n and 12 is very least as the input size keep increases. Okay, next is asymptotic analysis of an algorithm. This asymptotic analysis defines the mathematical foundation of its runtime performance. So using this asymptotic analysis, we can easily conclude the average case, best case, and worst case scenario of an algorithm. So we are going to deal with these cases: worst case analysis, average case analysis, and as well as the best case analysis. So this worst case analysis defines the input for which the algorithm takes a huge time. Okay, so normally the worst case is going to give the upper bound over there. We calculate the upper bound of the running time of an algorithm. We must know that the case that causes the maximum number of operations to be executed. But average case analysis, it is sometimes done. It's not regularly so considered for analyzing the algorithm. We take all possible inputs and calculate the computing time of all the computing or running time of the for all algorithm for all the inputs, and sum of all is calculated, and finally we are going to find the average values for that. The next one is nothing but the best case analysis, but it is this is nothing but an bogus value. Actually, it is define the input for which the algorithm takes the lowest time over there. Say for example, I can give the best case analysis means, say for example, you are given an array. In the array, you are going to search for a particular element. Okay, suppose if you are going to use the linear search for finding the element, say for example 22, if the 22 is present at the beginning of the array element itself, mean that okay, so this is going to become the best case value, because in the first iteration itself our search operation is completed. Suppose if the searching element is going to is present at the end of the array, so you need to go through all the previous memory locations, so that this is going to give you the worst case analysis. Okay. So the example for the best case analysis is nothing but the linear array search. The commonly used asymptotic annotations used for calculating the runtime complexity of an algorithm is as follows. First one is nothing but big O notation. It is nothing but a capital O, omega notation. This is capital omega, and big theta notation, and is represented by using the theta notation. Let us look into these one by one. I'm not going to discuss all these things very in detail. Just brief introduction to this we are going to give. First one is nothing but the big O notation is used for the algorithm analysis. Big O notation is an asymptotic notation that measures the performance of an algorithm by simply providing the order of growth of the function. It measures the worst case time complexity, or the largest or the longest time of an algorithm can possibly take to complete. This notation, as I already told, it provides an upper bound on a function which ensures that the function never goes faster than that upper bound. So it gives the least upper bound on a function so that the function never grows faster than this upper bound. This is nothing but the formal way to express the upper boundary of an algorithm. It measures the worst case time complexity, and this is represented as shown in this figure. If you look at this one, this is the function f of n. Okay, function. The upper bound is nothing but c into g of n here. Okay. For example, if f of n and g of n are two functions defined for positive integer, then the big O of f of n can be defined this way. Big O of f of n is equals to big O of g of n. There exists a constant c which is greater than 0, and there exists a number n naught. N naught is nothing but a number n. Okay, such that the function f of n is less than or equal to c into g of n for all the values of n greater than n naught. If you look at the diagram at this point here, for the value of n with n is equal to n naught, for all the value of n which is greater than n naught, your function f of n takes less time compared to other function, it is denoted as c into g of n, c into g of n. So that is c is nothing but a constant arbitrary values. Say for example, let us consider the example here. I have a function, say f of n. The f of n is nothing but, say for example, 2n plus 3, and I given another function g of n is equal to n. Okay, we wanted to find is f of n is nothing but big O of g of n or not. We wanted to find this. Okay, it means that we wanted to prove this f of n less than or equal to c into g of n or not. Okay, so what we can do, we know that the given f of n is nothing but 2n plus 3, 2n plus 3 less than or equal to c into g of n, that is nothing but n. Now assume that your c is taking the value 5 and your n is equal to 1. In this case, what will get? 2 into 1 plus 3 less than or equals to 5 into 1. Okay, actually this is 5 is equal 5 less than or equals to 5 only. This was code. For n is equal to 1, this particular condition, okay, that is f of n less than is equal to, say, c into g of n is the true. Suppose if I take n is equal to 2, and in this case you will get 2 into 2 plus 3, which is less than or equals to 5, the c value is equal to, I have taken c is equal to 5, that is into 2 here. Okay, so 7 is less than or equals to 10. Okay, so for n is equal to, and the above condition of above condition is also the true here. That is f of n is equal to f of n less than or equal to c into g of n here. Okay, we know that for any value of n, it will satisfy the above condition, that is 2n plus 3 less than or equals to c into n. If the value of c is equals to 5, okay, then only this is Morse code. We take any value of n starting from 1, so it will always satisfy. Therefore, we can say that for some constant c and for some constant n0, for some constant n0, it always satisfies 2n plus, it always satisfies 2n plus 3 less than or equal to c into n. So next is nothing but omega notation. It is basically describe the best case scenario, which is just opposite to the big O notation. It is the formal way to represent the lower bound of an algorithm's running time. It measures the best amount of time of an algorithm that possibly takes to complete, or the best case time complexity. It determines what is the fastest time that an algorithm runs. If you require that an algorithm takes least certain amount of time without using an upper bound, we use this big omega notation. That is, it is used to bound the growth of running time for larger input size. Let us consider that if f of n and g of n are two functions defined for positive integers, then we can say that big omega of f of n greater than or equals to g of n, there exists a constant c greater than 0, and there exists a number n naught such that the function f of n, the growth of function f of n greater than or equals to c into g of n for all the values of n greater than or equals to n naught, and this is depicted in the figure here. Okay, if you look at this diagram here, at n is equal to n naught, okay, the function f of n is the growth of the function f of n is greater than the c into g of n, means that it is going to give you the lower bound of an algorithm. Let us assume that, let us consider another example, same example here also. I have taken f of n is equal to 2n plus 3 and your g of n is equal to n. Okay, we ought to find out whether f of n is big O of g of n or not. Okay, so that if you say that it obeys this function, this condition means f of n should be greater than or equal to c into g of n. Okay, now let us check this. I check here 2n plus 3 greater than or equals to c into n. Okay, suppose I take c is equal to 1 in this case, so that my function will become 2n plus 3 greater than n here in this case. Okay. Okay, so this condition is true with the starting value n is equal to 1 itself. Suppose if n is equal to 1, this becomes 2 plus 3 greater than n. This holds good. Suppose n is equal to 2 here, so this becomes 4 plus 3 greater than 2, and so on like that. So as we can see here, the function is the lower bound of the f of n. This gives the lower bound of f of n when the value of c is equals to 1 here. Therefore, this big O notation gives the fastest, big omega notation gives the fastest running time, but we are not more interested in finding the fastest running time. We are interested in calculating the worst case scenarios, because we want to check our algorithm for larger input, that what is the worst time that it will take, so that we can take the further decision in the further process. So the last notation is nothing but the theta notation. It is also called as a big theta notation. The theta notation mainly describes the average case scenarios. It represents the realistic time complexity of an algorithm every time an algorithm does not perform worst or best. But in real world problems, algorithms mainly fluctuate between the worst case and also the best case, and this gives us the average case of the algorithm. Big theta is mainly used when the value of worst case and the best case is same. It is the one of the formal way to expose both the upper bound and as well as the lower bound of an algorithm. Okay, so this is the pictorial representation of this big theta is given by this, is given in this here. Okay, this goes the shows the growth of the function f of n in terms of c2 into g of n and c1 into g of n. Suppose if f of n and g of n are the function, then theta of big theta of g of n is equal to f of n. There exists a passive constant c1 and c2 and another number and a number n naught, such that okay, c1 dot g1 greater than or equals to 0 and c2 dot g of n. Okay, means that f of n grows faster than c1 dot g of n and lesser than c2 of g of n. Okay, we can able to take the example for this algorithm. Say for example, I say f of n is equal to 2n plus 3, the same case I am going to take, and my g of n is equal to 2 in this case. Okay, we would like to verify it, okay, whether this following condition is true for this big theta notation or not. c1 into g1 of n less than or equals to f of n less than or equals to c2 into g of n here. Okay, so if you replace these values here, you'll get c1 into n less than or equals to f of n, that is 2n plus 3, and less than or equals to c2 into n, because this is f g of n is nothing but 2 n in this case, not 2. Okay, so c1 into n less than or equal to 2n plus 3 less than or equal to c2 into n here in this. Suppose if you consider the constant value as follows: if c1 is equal to 1, which we already discussed in the previous cases, and c2 is equal to in this case 2, and n is equal to 1 in this case. Okay, so that if you apply these values in this case, you'll get C1 is 1 into 1 less than or equals to 2 plus 3 less than or equal to C2 is also C2 is equal to 2 in this case, so that 2, okay, so that we have this implies that 1 less than or equal to this 5 less than or equals to the 2 here. Okay, so that it satisfies this particular condition. For this value C1 is equal to 1 and C2 is equal to 2, n is equal to 1, this is going to satisfy this condition. Suppose if I take n is equal to 2 in this case, so this is going to be 1 into 2 less than or equals to f of n, that is 2 into 2 plus 3 less than or equal to C2 2 into n, that is nothing but the 2 you'll get it. Okay, so that you'll get 2 less than 7 less than or equals to, that is nothing but 4. Okay, again this also satisfies the condition C1 into g of n less than or equals to f of n less than or equals to C2 into g of n. Therefore, we can say that for any value of n, it satisfies the condition C1 dot g of n less than or equals to f of n less than or equals to C2 g of n. Hence, it is proved that f of n is big theta of g of n. So, this is the average case scenario which provides the realistic time complexities. Okay. Yeah, this is about the this is about the just introduction to the algorithm and as well the data structures, and from now onwards we are actually going to deal about how exactly the data structure can be implemented for the real world examples. Okay, so next session will be taken by the Dr. Ramya madam. Madam,
Namaste,
over to you, madam. Over to you.
Okay, sir.
Okay, thank you all.
Thank you, sir.
Any question for the sir part, whatever the algorithm? I hope it is clear. Any doubt you can ask him. Meanwhile, I'll share the PPT.
Yeah, if you have any doubts, you can able to, if you could not able to raise it now, you can able to put it over the team, so that I can able to try help you out in clarifying your doubt. Okay. You can, madam, I just stopped recording and you can able to start it once you start. Okay.
Okay, sir. I'll do that. Student, is my slide is visible to you? Am I audible?
Yes, ma'am.
Okay. Is the slide is visible? Yes?
Yes, ma'am, it is visible.
Okay. Okay. I hope it is audible and my slides are visible to you. Okay. Good morning to all. I'm Ramya. I'm from ENC department. So I'll be again talking about more on the more detailed information on the data structures and the algorithm. Now, first of all, we'll go with, as the sir has told, it's a basic. He has given a lot of example on array also. So we'll start with the array as a data structure. So it is already well-known structure for you. You already know a basic concept of an array. So what is this array basically? Array is a container because it holds a particular set of data. And you already know this is a fixed number. Okay. And it is also very important to know that it holds only the same type of information. This is very important. So it holds a similar, same type of, if you declare an integer array, it can hold only the integer value. That's what it means. So it can hold a same type of data. And what is another, as the sir has given already, when he was discussing about the worst case and the best case scenarios. So elements in the array, it holds a continuous memory location. So that's the reason when you are doing an insertion or deletion, you require to make a lot of iterations. Okay, so these are the important point. One is it holds the same type of data, as well as it uses a continuous memory locations. Okay. And what is the third information? It is mostly used, most of your data structures, we use your array as the basic structure for that to store the information. Now let us see more on this array structure. So as it is already mentioned, it contains two important points. One is element and an index. So please note in this diagram, so array is nothing but a container for this. So it has got 4 elements. It can contain a same kind of, it may be a character, or it can be integer or a float. Those are known as elements of that. Another important point is index. What is this index? How the numbering, the element, how they are referred with this. So pay attention to this. If you are implementing with the C++, your index number which you are trying to retrieve this element, it will start from 0. Okay, so though it has contained 4 elements, the last index is nothing but a 1 less than that. So it starts from 0 and then the 1 2 3. So be careful about this. In MATLAB representation, it is a different, because it starts from 1 there. So pay attention, whichever your program you are using, you require to know the how the index has been referred in that. So I'll go with the C++ concept only. So in this case, the index starts from 0, and the last index, you should be able to know that the number of element, whatever you say 4 elements, index will be less than that, 1 less than that, because it starts from 0. Pay attention to this information. Now let us take more detail. I'll be going with more with the one-dimensional array. We'll see when we require a two-dimensional. Okay. So what do you mean by one-dimensional array? As you know, one-dimensional array can be represented, or you can query by one subscript, a of 0 or something like that. So it requires only one subscript to get the information or put the information. So as you know that any your data structure can be implemented by any languages. It should be indifferent to the languages. But I'm trying to give one example. So already you may be knowing this. This is how we declare an array. So first we'll go with the data type. Then we'll give the name for that array. Then we'll define what is the size of that array. Okay. So if you just go with the definition, then I'm trying here the int, that is nothing but type of the array. The name, AR or whatever, you can give any name here. User defined values, okay, variable name. So this is specifying what is the container name for that, okay, and how many elements are there in this. This is nothing but a size of the your array. So in this example, you have to start in a C++ way of representation. If you want to initialize the array, you require to start with your curly bracket and give your element separated by the comma. I hope you know this way of representation in a C++. So in this case, you are defined these element. It is unordered. Why unordered? I can store any value. It is not a sorted value, so it's not in ascending or descending kind of. It is unordered, so you can define any element here. But observe, all belongs to the same kind of integer value. So integer, this is array name and a size of this. Now what about the index of this? Though I say the size is 10, but if you see the index of that, it runs from 0 to 9. pay attention to this. Okay, so whenever you're retrieving the element more than n, the size, then it gives an error for you. Okay, so you can't access array of 10th element because you don't have an index for that. Okay, so pay attention to this. Okay, now let us take the declaration. As we have already shown the declaration where we are trying to say the integer, whatever the type of that, name of the array and the size of this. But you can do a initializing of your array in many ways. Okay, so this is one example. So when I'm define the size of this, immediately I'm giving the value to this, whatever the container, whatever the values in each element. Okay, now, in this case, this is example, we can see it is also integer, but I defined the size 6 elements, but I defined only 2 elements. I've given only 2 values to the first 2 values. Now, what happens to others? It is by default, it takes a zeros. So this is another way of giving an element. In the this is a place where you while initializing itself, you are giving an element values. But this is also from another way where scene is nothing but from the your keypad or from the user. You are trying to take the element. You are accessing now area, that array part. Okay, so array, how I can access array? Give the array name and put in a square bracket element of which element you want to access. Okay, so this is a notation to access any array element. Now similarly, I can use a, this is how I'm trying to take all the element. I'm just trying to insert these kind of information. I'm trying to store the values. Now directly I can also access the information whichever is stored at the third index of the your array. So just provide element of that and I can store back to the whatever the variable. Similarly, I can assign the values at the particular index type. Okay, so these are the some of the array which you already aware of how to handle the array operation. Now let us take more detailed part. So as sir has told earlier also, so in case of data structure, we have to have a basic operations. So these are the basic operation which should support by the any data structure. Now let us go with one by one with respect to arrays. So as sir has already informed you, so the first case is very simple. You are trying to traverse through whole array and trying to, you think of an example where you want to print all the array element one by one. You are required to, this traverse is nothing but you are trying to access each element of the any data structure. So here it is an array for us. Now insertion, as already known to you, you are trying to insert a particular information at particular index value, okay, particular position. Now deletion is just the reverse of your insertion. You're trying to delete the content at particular point, okay, index of that. Now how about the search here? Search is nothing but you're trying to see whether the required element or information is available in the given data structure, that is array. Okay, now what do you mean by update here? You're trying to replace the at particular index. So you're trying to you are not changing any element other than the whatever the index value. So you're just trying to go point to the particular index value and replace it. Okay, assign that particular value. So if you observe this, in a first case you are not changing any length of that. Okay, there is no change in that. Okay, but in case of insertion, you are increasing the, or your array size is, you are inserting a data there. In a deletion, you have a change in your length. But in case of search or update, you are not doing any kind of changes in the length of that. Okay, so you can see this in a traverse or the search or update, you are not altering the length of that. Okay, but whereas in the other two, you are changing the, altering the values of n in the sense length of that. Okay, Now let us take a very simple, which is already known to you, a traverse example. So let a array be declared as a and it is of 15 element. But you observe this, I have declared only few of them. I have not declared all the other 15, all the elements. So it is by default, it will be assumed as a zero set. Okay. So what is happening if this is a traverse exam? So I want to display the content of a particular up to only up to 5 or up to 10 or up to 15. That is a maximum value I can go about this. So in this case, I'm just going with the only 5 element, but you can increase up to 10 or up to the maximum limit 50. Okay. So this is one example for your traverse. It's a very simple example. Now let us, this is very important for you. So this is nothing but a insertion operation. So what do you mean by insertion? By name it says that you're trying to insert or you're trying to add a particular information here. Insert one or more data element into array. We'll take an example where you're inserting one element. This element can be added at the beginning or the end or at a particular given index. Okay, so it can be the algorithm, when you say, it should be suitable for any of these operations. So you're trying to add an element, it can be at any given index. Now let us see how we can go about this. So this is the algorithm. What do you mean by algorithm? Algorithm is a piece of a set of a flowchart or a flow of information where it can be implementable by any languages. It should be indifferent to the languages. So what do you mean by here? I've taken one example here. So let there be a array which we call linear array, which is unordered. Unordered means it can be in ascending, it need not be in ascending or a descending order. It just the values, elements are stored. Okay, and there are n number of elements in that, and you're trying to insert at the, as you told, we already known that it should be workable for any index, whichever index you are trying to insert, but it should be less than the n, the size of that array, because you know that it is a fixed size. We are trying to insert, it should be less than that. Okay, now what is this item? Item is nothing but the name or number which you want to replace, or data which you want to replace, or you want not the replace, sorry, you want to add at the particular index. Okay, so let us take one example. Let there be a array something like this. Okay, just it's unordered, you can think of, there are the some numbers, it is an integer array you can think of. Now what is these are the index of that particular array. So it is at the 0th index, the 31 is stored, and at the 4th index, that is the 5th element, basically 4th element, you have a particular information is being stored. Now I want to insert 70, the integer value 70 at this particular point, say for example. Then how, so that once I insert, my array should look like this. So my array will be, I'm inserting particular information at the given index, whichever I wanted to insert, and whatever was stored in the this particular index should be shifted here, and the 56 should be shifted, and the 1 should be shifted to the next element. So I'm trying to shift this downwards. Okay, this is the algorithm which we are going to follow. Now how we can go for an algorithm, a set of instruction. Let us see this. So you're starting this. So you're setting a variable, say j, which is nothing but your n minus, because the element, number of element, as you know, is less than the one less than your index. Okay, so elements are more here. Say if I got 5 element, but if you see the index number, okay, is 4. So I'm trying to set a particular value, which is nothing but a maximum element. How many elements are there? 5 elements, and setting it to the 1 minus of that, because the index starts at a 0. Okay, so I'm now increasing the array size. Once I insert, the array size is going to increase by 1. So then what we are trying to do, we are repeating these two steps. What are those two steps? We are trying to put a, see, I want to insert at this particular index. So I'm trying to shift this element one by one. To shift this, first I have to shift this particular, the higher order element to the one place which is we require to increase. So I'm trying to, already j is set to 4. So 4 plus 1 is nothing but a 5. At the fifth element index, I'm trying to insert whatever was there at the fourth place. So I'm just replacing, I'm trying to shift towards this particular point. Okay, then what is done? J is decremented. So J, previously it was at this position, now I am trying to decrement, so it will be holding now 56. So these 2 points, or these 2 points are repeated until this condition is met. So in next iteration, you can see j is at this particular value. So at the 50, whatever this 56 is stored back to the fourth position, and j is now decremented by 1. In the next iteration, so whatever was stored at the your 44, this particular 44 is going to be shifted to the third position. Then you are trying to make a j decremented. But when the moment j is decremented, you can see this condition is not holding. So at that point, it will come out of this loop and try to go for a 6 here. So at that position, because you are vacated this, right? So you are trying to make a, now at this position, you are trying to insert the new element, whichever you wanted to add. Okay. So this new element can be anything, but it should be same as the element type. Okay. Data type. So you are trying to add a element at this particular given index, and you are updating that information. So this algorithm works for any of the languages. So you can use this particular set of instruction or the algorithm for the any languages. This is how any array can be, we can insert any element in your array. Okay, I hope it is clear. Any doubt in this particular, students? Any doubt? Is it clear for you? It's a very simple. You can also try with any of the your examples, or even in a C++ or Python or any kind of language. It's fine. Any doubt in this particular information? Students, can you give me a feedback? Yeah?
No
doubt?
doubts, ma'am.
Okay. Sir, shall we stop here, or shall we continue for other parts, sir? Students, shall we stop at, now it is 10. Shall we stop, or shall we take 2 more information on arrays? What is your feedback? Shall I continue for 2 more minutes? Or shall we take this information in our next class?
I think it's better if you go for the next class because some students are not there in the class.
I'm not, your audio is not clear. Can you, hello?
Some students are writing OTs of some companies, Bosch and other things. So a lot of students are not there in class.
Okay.
But we take in the next class.
Okay, then no issues. So we have, in this case, we started with just with the data structure, this array. So I'll stop at this point. So this is nothing but we have done only one part of the array information, that is nothing but insertion of any data. Okay. So I'll stop at this position, so that in the next class we'll continue from the your array insertion, and the next part will be the deletion and so on and so forth. Is it fine? Okay. Yeah. Any other doubt? If you have any doubt related to this insertion, you can ask me. Okay. Hope it is clear. Is my face is fine? Is it I'm fast or slow or something? Is it fine? Is it okay? Okay. Anytime if you have a doubt, you can always stop me here. So today's class, I'll just wind up at this position. Thank you. So we will meet again on the Tuesday class. Is it fine? Okay.
Yes, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you all.